Good morning, everyone, and welcome to the fourth and unfortunately last day of the Chaos Communication Congress. The opening speech for today in this room will be automated botnet detection and mitigation. And we've got with us today Georg Wicharski, who's been doing some extensive research on, well, malware in general and has intensified his research to botnets. And he's going to give us some ideas of how to detect botnets, how to analyze them, and the most important part, how to get rid of them again. Enjoy.
Thanks. First of all, unfortunately, the day before yesterday evening, my laptop somehow disappeared here at the Congress, so I have to present a different set of slides I presented at Black Hat Asia this year, together with Thorsten Holz. So these slides are not the ones I wanted to present originally, but there's a high amount of slides who have the same content. So this talk is now called Catching Malware, but it's essentially the same content. First of all, what is our motivation to catch malware? Why do we want to track botnets, and why do we want to mitigate botnets? Then we'll have a look at our tools and techniques we currently have developed to learn more about botnets, which is first of all Nepenthes for malware collection, CW Sandbox for automatically analyzing the malware we've collected so far, and BotSnipD finally for tracking the botnets we have found with Nepenthes and CW Sandbox. And then I'm going to present some results. So our motivation for botnet monitoring is we want to find new botnets, and botnets are a severe threat to today's internet community. Well, they are still a threat for several years now, but media attention has now come to botnets a lot more, so it's become a buzzword for most marketing people. And what is a botnet? Well, a bot spreads like worms. So this means they can not only by the nefarious purpose the botnet herder can have, they can take down machines, but simply by spreading like worms, they can already exhaust network resources and therefore take down a whole /16 in a time. So how do we get new botnets? Since it spreads like a worm, we can observe the infection and then take the bot that has infected our honeypot, analyze it, and then we obtain the information about the command and control server. And then we can track the botnet and eventually take it down. The typical communication flow for an ISC botnet is depicted here. I have no laser pointer, unfortunately. But you see here, we have a central, this is for an ISC botnet, a central ISC server, which doesn't have to run on a default ISC port. We have several bots, which are infected machines, which listen to the commands on the central ISC server. And we have an attacker, which is also often called the herder, who issues the commands in some whatever syntax that depends on the bot family to the botnet server, which then distributes it to the different bots. So how do we collect our malware? We have developed last year a low interaction honeypot daemon, which is a POSIX daemon, which is called Nepenthes. So with this daemon, we can automatically collect the malware, for example, like bots, but also normal worms which don't have a command and control infrastructure. And we do that by emulating known vulnerabilities. So this is a severe limitation. We have to know the vulnerability which the bot is spreading with before we can actually catch the bot. This daemon is released under the GPL license, now available in version I guess 0.2.0 at nepenthes.mwcollect.org. So this daemon has a modular architecture because we realized as there is a lot of new vulnerabilities coming out each month, we need to have a simple way to extend the daemon. And we have separated the work which is to catch a single bot into different kinds of modules. First of all, there's vulnerability modules, which actually simulate the real vulnerability. Of course, then there's the payload and the vulnerability, which contains a shellcode. So we have shellcode handlers, which analyze the shellcode. Then we generate some generic URL from the shellcode, which doesn't have to be an HTTP URL. It can be any kind of URL. So we have download modules to actually download the malware from a central distribution server or from the attacking host. Depends on the bot again. And we have submission modules to take care of the downloaded malware and spread it in our collection servers or whatever. And additionally, we have an event system to automatically generically trigger events. And we have a shell emulation and virtual file system, as a lot of bots or malware for attacking relies on the Windows subsystem, like the Windows command shell. So this is a schematic overview. As you can see on the left, there's the Nepenthes daemon core, which is the only executable file in the layout, so to speak, which opens the different ports and then associates them with the different vulnerability modules. Of course, there can be multiple vulnerabilities on one single port, so we have to do it in the core itself, so we have multiple modules per port eventually. Then we have the payload stage. The payload gets forwarded from the vulnerability module to the shellcode handling modules, which means since we have a generic interface, we can have any shellcode we know can come in over any vulnerability we know. So this means we can have a much higher coverage of shellcode vulnerability combinations. The shellcode modules rely on, analyzation modules rely on the Windows emulation, as there's often shellcodes which contain a tftp.exe command line simply or something like that. And then we have the URL of the malware generated, which is then getting forwarded to the download module to actually obtain the malware we've just learned about. And if we've downloaded the binary, we can submit it to the local file system with the submit file module, or submit it automatically to the Norman Sandbox or to an XML RPC server, whatever suits you best for your personal setup. So looking at the modules in detail, first of all, the vulnerability modules, of course. As I've said, we have only an emulation of vulnerability services. And we don't simulate services to the whole extent like what a service supports. For example, there's the LSASS vulnerability in the Windows SMB implementation. And of course, we don't implement the whole Windows SMB subsystem, but we only implement of the daemons or services we emulate the amount we need to emulate. So we look at common public exploits, look what they require in functionality, and we only emulate that. So we have some kind of finite state machine. So if an exploit expects a certain response, we give it that, but we don't have the whole service functionality. Currently, it's more than 20 available vulnerability modules, ranging from the old but still often exploited LSASS vulnerability to recent cymatics vulnerabilities, but that was even after this talk. So yeah, we always continue to develop more as some exploits are not exploited anymore and so on. So as I've said, we need to know the vulnerability in advance, and we need to manually analyze the vulnerability and the exploit for it, which is a lot of work. And we're now working on automation, which is not these slides, unfortunately. So what we do is and we work with Corrado Leiter from the Institut Euricom in France. He's working on software called ScriptGen, which can automatically, if deployed in front of high interaction honeypots, generate state machines of the exploits. Yeah, this is a bit difficult to explain without the slides, but you have a software running in front of the high interaction honeypot, then you can see different attacks coming from different hosts exploiting the same vulnerabilities, and using some genetic algorithms you can learn the vulnerabilities, so to speak. So we found a way to at least generate these state machines we have for the exploits automatically, and we're working on a setup to do this in real time on the internet. With perhaps a delay of 2 or 3 hours, we can then catch even malware which is spreading through zero-day vulnerabilities. Yeah, here's an example of one of the oldest and traditional, so to speak, vulnerability modules. This is the LSASS exploit, which is one of the most exploited vulnerabilities even today because it's very reliable, and there's a lot of old boxes which don't have it patched even today, so it's often used still. And as you can see here, we just have the exploit here. It sends some data, some pre-generated requests, then receives some data, doesn't look at the received data at all, and then sends the next request. So for this simple case, our vulnerability module, which is not from Nepenthes but MW-Collect-D, the predecessor of Nepenthes, looks like this. no matter in which stage of the exploit we are currently, we just send some random garbage back to the host and at once into the next state, and this works with all known bots, because bots are like, most botnet herders, or a lot of botnet herders, are not too good at coding, so they take the public bot source, take a public exploit, somehow mod that exploit into their bot source, and you end up with such a cheap emulation which still works. Yeah, a brief overview about the vulnerability modules is we have one for the old DCOM and Altus vulnerabilities. As I've said, they are one of the most exploited ones. We also have ASN1 and WinS, which go to, against the IIS server, and also some WinS is, of course, the hyped Windows 2000 vulnerability. These are also a lot exploited because they are more not against like client machines, but against Windows servers, and there's still a lot of Windows servers which don't have these vulnerabilities patched. Well, because if I say a lot, this means it's a really low percentage, but looking at how many computers are on the internet, it's still a relatively big absolute amount of computers. This is probably enough bandwidth for any botnet herder he wants, so they stick to these old exploits. And there's a lot of other exploit categories. For example, we have some other server exploits there, the MS-SQL exploits, and we also have, what is quite funny, some vulnerability modules which actually emulate backdoors or exploits in older malware. For example, if you look, there's Bagel and MyDoom, and both Bagel and MyDoom had a backdoor for the malware authors to upload new malware, but then other botnet kiddies found out how these bot backdoors work, and then they spread their bots on already infected computers via the backdoors of other malware. So we wrote these vulnerability modules to catch these as well. And we, of course, have the Veritas vulnerabilities and a lot of more. So once we've been attacked, we now obtained, by cheaply emulating the server somehow, the payload, which is in nearly all cases a shellcode. And we need a way to find out how, with this shellcode, the malware wants to infect the computer. So we have, first of all, most shellcodes have some restrictions, like there may be no 0 bytes or whatever. If you have ever dealt with shellcodes before, you're probably familiar with the principle of decoder headers. So what this is, you have a simple shellcode which is encrypted, and you have a very short assembler code in front of the actual shellcode which decrypts or decodes, or however you want to name it, the actual shellcode with some simple XOR or whatever. So we have some generic XOR patterns. This is actually PCRE patterns we're using for that, which detect which encoder is being used, extract the key, and then we can de-XOR them ourselves. And then in a second stage, so to speak, actually we loop endlessly here more or less to a certain extent you can configure. So you can have a decoder which decodes a decoder, which decodes a decoder, and so on. But anyway, in a certain stage then there comes the actual code which would then download the malware on a real machine. So there's some, for example, some generic create process shellcodes or signatures we have which match most create process shellcodes. We have signatures which may just generically match an URL, because once we've decoded the shellcode, sometimes there's just an HTTP or FTP URL in plain text in the shellcode, which at some point gets pushed or whatever on the stack, and we can just match against it, and we have already the URL with not too much work. And the same goes for some generic commands like tftp.exe, ftp.exe, which are used, and we can grab these in plain text as well and then use. So this is an example of one of the bots using a command shell code. First of all, it just uses a bind shell. Oh no, this one has the commands embedded. That's clear. So this one just invokes the create process API on Windows using the following parameter. It's just one parameter. So it echoes a control file for ftp.exe into a temporary file called II, and then invokes ftp.exe with some parameters, like you see -s means it shall use the file it created before as a command file, then deletes the command file, and then invokes the downloaded file, which is called svc